Thank you. So I'm starting a little bit over what you're interested in. It's okay. It's more technical detail, but what we're interested in is the composition of Mercury, and the reason why we can learn something about the origin of Mercury, we can learn something about the evolution of Mercury. And this is, of course, complicated because what we can see is the surface of Mercury. And the surface of Mercury is not. Mercury has a core, a solid inner core, a molten outer core, and it has a mantle, and on the top of the mantle is a crust. So we see the crust, or perhaps we can see the crust, but what we actually see is the surface, and the surface is not necessarily the crust. And so we measure the composition of the surface, hopefully. And we measure the composition of the surface by two means. One is the exosphere, so there's no atmosphere of Mercury like the moon. It's an exosphere, meaning it's so thin that all the material in the exosphere comes directly from the surface of the planet. So whatever we measure in the exosphere comes from the surface, so it reflects the composition of the surface. And then by remote sensing, we can also measure the surface itself by the infrared spectroscopy. Of course, the exosphere promotes transport of particles, so we have to see how species migrate in the exosphere. Maybe they accumulate at some places, so that would change the surface composition. And so this is more or less the topic of what we're talking today. So when we talk about the exosphere, when we have processes which populate the exosphere, particles stay in the exosphere between 100 and 1,000 seconds. If we don't do anything, when we fall all back to the ground or escape into space and when it's empty. So you need permanent processes populating the exosphere. And so here are the four major processes we have been discussing over many, many years. One is micro-meteoroid impact vaporization. So you have micro-meteoroids hitting the surface here. We release material, we release smaller grains. Also, we release atomic species, we release molecular species. So it's kind of a thermal process at elevated temperature. Most of the stuff here, it's just sodium, but there's also reflective of other species. Most of the stuff falls back onto the surface. Very little escapes from the planet by gravitational escape or being analyzed and becoming part of the environment. And the thermal desorption, Mercury surface is hot, so it's volatile, and sodium is one of them. Evaporates, most of it again comes down, lands on the surface, and a very small fraction leaves the surface. When we stimulate the desorption, a process which is very selective for sodium and potassium, again, most of it comes back to the surface, a very small fraction is then lost from the planet. And the most energetic process is sputtering. It's hit by solar wind, by ions hitting the surface, releasing particles from the surface. A large fraction is lost, some part of it comes back to the surface. That's already indicated in the surface is regolith. So this is into smaller and smaller pieces by impacts from micro-meteoroids and also large. So we have now surface layer, what we call ambient population. So things which fall back, in that case it's sodium, but also other species, land on the very surface. So we make a coating of the surface. We might evaporate again and come, and so we might migrate. So the very surface may be already contaminated by these processes, and not exactly what you want to know, composition of the regolith or crowd. We also have to look at the depth. So also looks at the very surface. So we come from the top few monolayers, particles are released. Evaporation comes from the surface, but it may be diffusion, which produces
recording in progress.
Produces particles from the inside being thermally released into the atmosphere. Micro-meteoroid impact goes a little bit deeper. It depends on the energy of the particles which come in, but also on the size of the particles. So these are the processes, and in the terms of composition, we are interested in sputtering, because sputtering addresses all elements. Everything which is on the surface, everything which is hit by and eventually released into the exosphere can be measured by us, for example, by Strophe or by BepiColombo in orbit of Mercury. So this is in this process. And the second process is micro-meteoroid vaporization, because it does the same thing. You hit with the particle, the surface, a fraction of the released material is vaporized, these atoms and molecules of the material when you hit. And so you get also a picture. It reproduces somehow the composition of the surface. The other processes are more special, and of course, we are interested in the physics and to understand it, but it goes beyond today's scope. So let's start with sputtering. Sputtering looks simple when you do it at this cartoon level. So you come with a primary ion beam, so that's the solar wind, so like a kilovolt per nucleon, protons, alpha particles, we have in 4 kilovolt energies. We are heavier ions, but we don't contribute significantly to the sputtering because the abundance is very low. So we hit the surface, and you can have a simple ball model of the surface, different species, mature species, some other species. And then, because you have an impact of high energy particles, high in the sense of binding energies, you release stuff. You release neutral atoms, you release ions, negative ions, you release electrons. So we have super thermal energy, so we can go to quite some altitudes and make a large corona of parts around the planet. Sputtering has been known for centuries. So the first reports go back to the books, books on sputtering, detailed books with atmospheres. The software, Drip is a very popular software to use in our field. But there are many others, and I know in our work together with the group at the Technical University of Vienna, we use this SD-Trim. And so it gives better results, but it's a more complicated code, as usually with better results. Molecular dynamics codes like Marlow or Tridine and so on and so forth. So it's in principle a very well understood process because it's used in industry, sputter coating, micro machining, semiconductor fabrication, and so on. It's really well understood. So what happens with sputtering? What happens is you have this primary ion, it passes the surface, and here you are in the solid, and the ion makes a trajectory until it comes to stop. With every collision, it loses some energy until the energy is small enough, but it has to stop because it cannot move atoms in the solid. At the topmost layer, so you hit, for example, here, and you have a secondary particles, it may have a R, which makes it to go out of the surface and may kick out and so forth. But we come from up here. Particles which are sputtered come from the very surface. So here's some statistics. Where the sputtered particles come from the very surface, so the first monolayer, second monolayer, third, and so forth. So this is the very surface, and that has to be remembered. We get the information from the very surface. And remember, I told you, particles can fall back and go. So what do we learn? We have to understand the whole process, not just the sputtering. But you see, the trajectory goes on for quite a while. And so the second thing, what happens with the ion impact, is what we call space weathering. So the energy, it moves particles, so it changes the crystallographic structure, it destroys the crystallographic structure, it promotes migration, diffusion, and whatever. So the global term for it is space weathering, and we will see what it looks like. And again, look a lot on these processes, so we didn't invent it, we're just using it. So this is the space weathering. It has been discussed already 75 by Hapke 2001. And what you see here is a plug-in class unorthodox screen. So from a lunar, you see dimension 10 nanometers. You see surface and the rim. And so there's a rim here, the order of 30 to 50 nanometers. 30 to 50 nanometers is about the penetration depth of the solar wind ions. So we deposit the energy, we do harm there. And what we do is that we produce these nanophase metals, iron here. So the iron then coalesced, so it's very small, nano, so you see 10 nanometers, so with a nanometer sized metal grains. The oxygen is lost. So here you have another example here, and this is an agglutinate, so this is a gaseous sentence. If you have impacts, you create all kinds of stuff, but some of them are classic stuff. So on the moon, you have maybe 10% of agglutinates. On Mercury, you have 30 or 40% agglutinates, because you have further potential. Micro-meteoroids come with more energy. We can do more harm, so you get more glassy material. But again, you see this rim here about 15 nanometers. And then because it's glassy and so forth, you have a deeper layer here. Places of nanophase iron. But here is really the nanophase iron. So what does it to you? It darkens the grains, and of course it changes the composition. And this is where we get some of our information. By the way, it's selective loss of oxygen, so you can metallize one. You have to remove the oxygen from the crystal. We found out by helium-2 plus ions, so it's the second most popular thing in the solar wind. You selectively remove this oxygen by process potential sputtering. What we talked so far was kinetic sputtering, just potential sputtering is when you use the potential energy of this doubly charged ion to do damage. So here's a little bit more. This is again this same picture here in a larger magnification. You see the larger iron grains further inside and the smaller ones, which are just the direct result of the space weathering, the implantation, and the effect of solar wind. There's another one, again, such a high resolution microscopic image transmission electron microscope. You see these rims here. The color coding are different elements, and on the outside you see the metal, iron, and that makes the grains darker. And it may look like the whole planet is basically a metal sphere. But you see lots of iron if you only look that deep. You see the small grains, so this is the nanophase iron, and here you see the elemental composition. So the top grain is this blind blue class grain, and at the bottom we have a crystal polite grain. Don't ask me what it is, but it's another grain. But here the claim is it has the same rim. Whatever you have underneath, the weathering produces the same rim. They all look like the same. Okay, now I'm not going through these formulas in details, but with sputtering, we have a total sputtering. And so you hope that this total sputtering to the mass you have, so that you get kind of a one-to-one or a close one-to-one relation between what's on the surface to what's in the exosphere. There's, of course, an energy distribution, there's an angular distribution of the sputtering. So it's a complicated formula. But if you want to know more, so our long-term collaboration was mentioned. If you want to know more, ask Helmut. He's very close to you. And we worked with all kinds of detail, and so I don't want to elaborate on this here, but we understand the process really well. So what we don't understand very well yet is, so far everybody talks about sputtering. You promote atoms from the surface into the exosphere, you measure them, we know everything. If you look at this one, these are very old studies, 78, so 1978, different century of sputtering, low energy sputtering, so something really comparative to solar wind sputtering. And then you see, it's not just atoms, it's tantalum oxide, so it's an oxide surface, or niobium oxide, or tungsten oxide, and so forth. Double oxide. So you're not just getting the atomic species, you're getting molecular species up there in the atmosphere. Nobody talks about it, but look at that, it's significant. It's not like a small peak. We're talking about comparable amounts of material going up into the exosphere. Same thing was sputtering of oxides. If you look at ions, so here are ion fields, so the metallic ion, the single oxide, the double oxide, negative ions, and so forth. So when you speak out Rohan, Antalo, because we saw it before, so the metallic ion, the atomic ion, is supermetal. 10 times more, you get the single oxide, and still more for the double oxide. So if you are in the lucky situation to have the mass to measure ions, minimum. Energy distributions comparable to the atoms, so we go high up in the atmosphere, you don't have to get very close to the ground to measure the speed. There's an additional component. So sputtering is an energetic process, not just producing the energy, the kinetic energy with which we go away from the surface, but if you have a molecule, it has an internal energy as well, like a vibrational temperature, a rotation temperature. So if you have like substantial temperatures, and this is some lab measurement completely unrelated to our problem of space, but you see temperatures of a couple thousand degrees. You know, something at a couple thousand degrees will not stay in a molecule forever. And I told you, it goes 100 to 1,000 seconds for a simple trajectory. For a sputter trajectory, maybe 10,000 seconds because you go higher. In that time, they will fall apart. They disintegrate in atomic species. And then it looks like this. So you start, for example, with calcium oxide, because a colleague in the US is a very big fan of calcium oxide being released into the atmosphere. So you release calcium oxide in the atmosphere, and here you have the altitude above the surface, and here you have the density. But at some point, it falls apart, and then you create, oxygen atom and the calcium atom. And you see the slope here is much shallower. So this goes deep, it means cold temperature. Here you see higher temperatures or higher scale heights and so on, because you release the binding energy. So it seems like if you look at this calcium, it was released from the surface at much higher energy than it actually was, because here you get this extra binding energy. So there's lots of discussion how to interpret it or anywhere. But here are the measurements we did, and here's this model. So if you take this calculation, you see this model, so we can explain this density of calcium if you take it from here and compare with the measured data, and it looks quite favorable. The second process to learn about composition is micro-meteoroid impact vaporization. So you have particles which hit the surface with 20, 30, on Mercury 40 to 80 kilometers per second. So anybody of you who served in the military know that the gun gives you 400 meters per second, roughly. Maybe 1,000 if you have one very vicious instrument. Here we're talking 40 kilometers per second, so you can imagine what damage it does. And releases lots of material from the surface in this cloud. In steady state, looks like a cloud of this kind of temperature. So this is how we model it. And what you do is, so this is a microscopic impact, but it goes on all these scales. You impact, you make a crater, you change a lot of material here, which is not released. You have material which is released, macroscopic material, breccia, which you see on the lunar surface, which you also see on the Mercury surface. So material is released very high up, and then it falls down. And part of this material is in the gaseous state, atomic species, molecular species. And this is what we can measure with mass spectrometry in orbit. And again, all elements are represented. So we are not depending on diffusion. What also is important, the crater diameter rule of thumb is about 10 times the projectile. And the volume is 100 to 1,000 times, depending on the impact speed. So of course, you will also see the impactor in the gas plume. But it's 1 over 100, maybe 1 over 1,000 contributing to the whole gas. So the majority of the stuff you see is actually coming from the surface. And this is why we can use these impacts to analyze the composition of the surface. One convenient thing is we're going deep. So if you come with a 10 or 100 micrometeoroid, and this is kind of the bulk flux of micrometeoroid, you're going deep to maybe a millimeter. And so you overcome this changed surface. You vaporize a whole grain, and the typical grain size on the Mercury surface is about 60 microns. So you get really on this level of micro-meteoroids a bulk composition. So that's good. There's of course a time dependence. You have to have one impact after another to maintain an atmosphere. But what happens? So the micrometeoric fluxes of Mercury are substantial. The exact number is under debate. It's difficult to measure because you don't see it, you only see the atmosphere, you calculate basically back. So there's varying numbers within plus minus a decade. So take the number which fits your observation. Yeah, but if we have the smaller scale, it's still an impact. So here you see a grain, again, a lunar from Apollo 11, a grain, and that's about a quarter of a millimeter. And you see it's an agglutinate grain, so it was liquid at one point, so it's in gaseous state now. You have some weird impacts, but you also have like a poster boy impact, very nice, great, and so on. So you have these impacts on all scale. Part of it ended up in the exosphere as vapor of his impact. But because you have an impact, you create a plasma plume. You start out with about 10,000 Kelvin. When the plume expands, the plume cools off. And at some point, the density in the plume is so low that you don't have chemical reactions anymore. And this is kind of a freezing. And at the end, so maybe it's 3,000 Kelvin, maybe it's 4,000 Kelvin, whatever. When you reach the temperature and the density when chemical reactions are not possible, you end up with a composition. And here are the different traces of the species. Some are atomic, some are molecular. Sodium, potassium, for example, there's calcium. So depending what the end temperature is, you have a different composition. And again, they will decompose eventually. So we will see how close you have to go to actually see these molecules. But BepiColombo will tell us. So here are three different cases. So there's an aluminium and iron, and here you see nitrogen, CO2, and so forth. So this is a calculation our Russian colleagues did for the BepiColombo project. So this is what you expect to see, which we cannot see yet because messenger was not equipped for it, and spectroscopically you cannot measure this kind of stuff at all. Very short from our collaboration here with Graz. I talked about sputtering, micro-meteoroid impact vaporization for rare species. We did this calculation. You don't have to go to all these details. I want to just stress the point. The amounts you get into the atmosphere by sputtering or by micro-meteoroid impact vaporization are about the same, within a factor 2, 3, depending on species and so on. So these processes, and I picked out the two for this exact reason, they kind of equally contribute to the population of all these refractory species in the atmosphere. And so is why we discuss them. Now, as an example, what can we do with measurements? And this is a very famous measurement. It's the Gibbs instrument or messenger, which measured plasma composition. So you have your mass charge, you have the counts. And the team from Zurbuchen et al. Interpret this, of course, helium, implanted helium, which is released then, or what processed in magnetosphere of Mercury. When this bump here is the so-called oxygen group, which is oxygen, OH, H2O. And then this bump here is called the sodium group, with sodium, magnesium, silicon in there. And the last one is the sulfur group, which has O2, sulfur itself, H2S, for example, and so on. Okay, so this was their interpretation, and we did plasma physics with it, and it's all very nice. So this is Mercury's magnetosphere. It's very small. With Mercury, magnetic field makes a little magnetosphere to hold off the solar wind, the position of Mercury. And the penetration of solar wind is at the cusps here. So when you have a magnetopost height here, of about 1500 kilometers. So if you produce ionization here, you sputter, you get neutral salt, you ionize them, and then if you ionize them, you evaporate them in the electromagnetic fields of the magnetosphere. Why is it interesting? The thing is, the measurement, so it's a top view, bottom view of the trajectory of this flyby. The measurements were done on the night side of the spacecraft. So we measure ions here, which come from here. Okay, we can understand that. I don't want to go through the formalism, but because the curvature of the magnetic field is really high, because it's small, so it has to bend a lot, the convective field from the solar wind is high because you're close to the sun. So basically, the trajectories make it that the ions are all move back to the tail side, very close to the equator. And so this is where the trajectory will be. So that's cutting this story really short, but that's understood. And so what we measure here comes actually from here. So assuming that we did our here, we put the scattered density, so with the neutral densities, when you ionize them with the sun, and then you can produce, not fit, you can produce an ion spectrum. So this is not a fit. So you see here, helium released from the surface by that's thermal. But when there's carbon, here you see two peaks. There's oxygen, there's sodium and magnesium, and you see the magnesium peak is actually higher than the sodium peak, so it should be a magnesium group and not a sodium group. And here, silicon is indeed a silicon group, but there's also contributions from aluminum. And then here, O2 and sulfur, and then there's potassium, calcium, and so forth. So the blue line is all what we get from sputtering, and let's calculate that ab initio from the model, assuming a surface composition, which we derived much earlier. And then thermal is to make it kind of big. So you can then compare to what people measured, and so we can revise literature values, and some were very close here. Others were way off, for example, for the sodium. So what you get from sputtering. So you can calculate from these observations by this modeling density in the exosphere. You can do the same thing with the neutrals, with the thermal species here. Of course, scale heights are much lower. You ionize them, and when you get the thermal contribution, so these are the dashed dotted line. So here, for example, here the OH and H2O. So this is not a lot of H2O as you will see, and some other species like there's thermal sodium released from the surface. Remember, there's this surface coverage, and there's also some argon here. And again, you can compare to what people have published. In some places we still have an upper limit, but we have an upper limit which is much lower than what has been published before. So that's the exosphere. But the exosphere comes from the surface. And so we want to learn actually about composition of the surface. And the second set of measurements we can use is what we got from Messenger, is X-rays or X-ray spectroscopy and gamma ray spectroscopy and neutron spectroscopy. And just as a teaser, here are maps with magnesium silicon and aluminum silicon ratio on Mercury. What I want to say at this point is it was a highly elliptic orbit. It had this pericenter near the North Pole of Mercury, so you were close. And you have, of course, high resolution measurements near the North Pole, and on the South Pole, there was the apocenter. So the resolution was significantly less, and so you more have less of like global information parallel. Before we discuss this data, there's one thing we have to remember. What do we see? We have these different techniques. So I told you, sputtering, the topmost layer. So here you see a length scale, 10 to minus 10 meters. We go all the way to 100 kilometers. The sputtering comes from the very surface. X-space, not used in space so far, is very You could do it, yeah. Just when you're looking for the sample how you can break, it's the break on the particle. But you could do lots of plasma. Lots of uncertainty. What day before to learn something about it?